To stand on Mars would be to prove humanity can reach another world, but does that make it the next step, or just the most tempting distraction? When we talk about the future of humanity in space, one destination comes up more than any other: Mars. The red planet has captured our imagination for over a century, standing as the symbolic next great leap after the moon. If the moon was our first step, Mars feels like the first real stride, an entire planet, a world in its own right, waiting for us to set boots on its dusty soil and raise our banners beneath its pale skies. But is Mars really the next logical step, or is it just a romantic distraction pulling our gaze outward while more practical options lie closer to home? This is not a question of whether Mars matters, it certainly does. It's a question of how it matters. Today we will explore both sides of that coin, the reasons we should go to Mars, and the equally important reasons why perhaps we should pause, prepare, and focus on nearer, more useful goals first. This episode is not about how Mars is a waste of time, or a challenge too great to us. Neither is true. I've been both saddened and angered by the uptick in folks implying otherwise of late. At the same time, we must not go the other extreme and imply that only by going to Mars can we save humanity or reach out to further worlds beyond. Our grand ambition and road to the stars does not pivot on any one rock, not the moon, nor Mars, nor any other. And yet Mars holds a special place in our minds, at least in part because Mars is a world of paradoxes. It calls to us with dreams of exploration, science, and survival, but at the same time it may not serve the economic, technological, or strategic needs of a true spacefaring civilization. To understand why, we have to start with the reasons Mars has such a pull on us, the case for going. The red frontier in our imagination. No other planet looms as large in our cultural imagination as Mars. Since the invention of the telescope, people have squinted through lenses and imagined seas, forests, and cities on that distant red disk. In the late 19th century, astronomer Percival Lau claimed to see vast canals crossing the Martian surface, built by an advanced civilization to transport dwindling waters from the poles. That vision turned out to be an illusion, but it fueled generations of speculation and stories. C.S. Lewis's rare venture into science fiction. H.G. Wells imagined a Martian invasion in the War of the Worlds, painting Mars as home to a dying race desperate for Earth. Edgar Rice Burroughs' John Carter of Mars depicted a romantic and warlike society under a fading sun. Ray Bradbury's Martian Chronicles told poetic tales of contact, colonization, and loss. Through science fiction, Mars becomes our mirror, reflecting both our hopes for a second Eden and our fears of decline and conquest. In truth, Mars was not the sole focus of our dreams in that time. Venus was very nearly as talked about, but when in the mid-20th century we realized its clouds held not water but acid, and was not a paradise but a suburb of hell, I think Mars became almost a last ambition to interplanetary travel. Even today, as we discover countless exoplanets and ever more minor planets in our own solar system, Mars sits at the center of our imagination. Elon Musk speaks of making humanity multiplanetary by colonizing Mars. Indeed, I think his focus on it, and the hostility some feel for him, drives a lot of the newfound dislike for interplanetary mission in some folks. While there are many good reasons to favor or disfavor human missions, whether or not you like its advocates really should not be one of them. And he is hardly alone in such advocacy. Robert Zubin and the Mars Society dream of permanent settlements. Hollywood churns out films like The Martian or Ad Astra to put Mars in the spotlight. Children grow up imagining what it would be like to walk on another planet, and Mars, more than any other, feels within reach. The vast majority of the discussion of terraforming revolves around Mars as the subject of such efforts. This matters because inspiration drives exploration. We went to the moon not just because it was possible or necessary, but because it was stirring. Mars plays the same role today. It is the place we dream of, the poster child of humanity's future in space. Mars is a scientific treasure. Beyond the dreams, Mars has immense scientific value. Almost all of our knowledge of planets comes from examining Earth, and anytime you have one example of something, no matter how hard you try otherwise, you would tend to have assumptions and errors pop up in your work simply because you take things for granted. It is hard to see black swans in a world where only white ones are ever encountered, and we likely carry many assumptions from only being able to truly examine our pale blue dot that may be broken by intense study of the red planet. It's probably the best candidate in the solar system for finding evidence of past or present extraterrestrial life. Billions of years ago, Mars was warmer, wetter, with rivers, lakes, and perhaps even shallow seas. Microbes could have evolved there, and their traces might still be locked in the soil or trapped beneath the polar ice. Discovering Martian life, or fossils of it, would revolutionize biology. It would mean life is not a miracle confined to Earth, but a natural outcome of planetary chemistry. Mars is also a geological archive. Unlike Earth, with its plate tectonics and active weathering, or Venus, where the land is molten, Mars preserves ancient surfaces billions of years old. By studying its rocks, dust, and craters, we gain insight into the early history of the solar system, the evolution of planets, and the delicate balance that makes a world habitable. Its thin atmosphere and extreme seasons provide a living laboratory for climate science. In an era where we worry about our own atmosphere, Mars offers a comparative case study of a planet that lost most of its air and water. From a purely scientific standpoint, Mars is a gold mine. It combines accessibility, close enough to reach with current rocks, with profound questions about life, geology, and climate. Even if no one ever settled there permanently, the case for sending expeditions of astronauts and scientists remains very strong. A planet we can stand on. But Mars offers something beyond sight, a sense of home. Venus has crushing pressures and searing heat. Mercury is airless and scorched. The gas giants have no solid ground, and their moons, while promising, are shrouded in ice and radiation. Mars, by comparison, seems welcoming. It has a surface you can walk on. It has mountains, valleys, and canyons more dramatic than any on Earth. Olympus Mons, the tallest volcano in the solar system, towers 3 times higher than Everest. Valles Marineris is a canyon that could swallow the Grand Canyon many times over. To live on Mars would be to live on a world that looks like a frontier, an alien wilderness begging to be explored. Its day length is 24.6 hours, almost identical to Earth's, making circadian rhythms natural for humans. Its polar caps hold frozen water. Sunlight is weaker than on Earth, but still strong enough for solar power and farming under domes. Its gravity, at 38% of Earth's, is enough to stand, walk, and run without being confined to floating microgravity. It might not be healthy long term, we simply do not know yet, but it feels like a step closer to normal life. Mars offers the potential for local resources to bootstrap colonies. Carbon dioxide in the atmosphere can be cracked into oxygen and carbon monoxide. Water ice can be mined for drinking, fuel, and agriculture. Regolith can be turned into building material. It is not easy, but it is at least possible to imagine a closed loop of life on Mars in a way that is much harder on the airless moon or distant asteroids. The symbolic step. Finally, Mars represents something bigger than itself, the first real world beyond Earth. The moon is our neighbor, a familiar companion. Asteroids and space stations are platforms and tools, but Mars is a planet, an entire globe. To sell it would be to prove that humans can live not just in orbit or on outposts, but on another world entirely. That symbolic leap carries enormous weight. It says humanity is not bound to Earth alone. It says we can be a multi-planetary species. Even if the economic returns are poor, the symbolic and psychological returns are immense. They can inspire generations, unify nations, and provide a common goal that stretches our horizons. As humanity moves into a time of great automation and ever greater prosperity, we are even better suited than our ancestors to take on tasks that simply call to us, and they rarely flinched from those challenges, even though they had a fraction of the knowledge and resources we can bring to bear upon such tasks. A civilization in need of little needs one thing: purpose, and Mars stands ready to provide one, as an easier one to substantially tackle than any other planet in the solar system or beyond. The case so far. When you put all of this together, it is easy to see why Mars stands out. It's near enough to reach, alien enough to fascinate, survivable enough to imagine living there, and scientifically valuable enough to justify exploring it. Its cultural momentum is unmatched, its scientific promise unparalleled, and symbolism undeniable. If we were choosing our next great frontier based only on inspiration, Mars would win hands down. It is the Everest of space. Difficult, dangerous, and not terribly practical, but irresistible all the same. But as we'll see later in this episode, inspiration is not the only metric that matters. Dreams can propel us forward, but they can also blind us to reality, and the reality of Mars is harsher than many realize. The case against Mars. For all its charm, Mars has a great deal stacked against it, especially in the near term. The simple truth is that we are not ready, and readiness matters more in space than anywhere else, because unlike Earth, failure off-world is seldom survivable. That said, I do believe we could create a mission there, even today, at a price that would not bankrupt the US nor be guaranteed to fail. However, as we go through these options, we ask not if we could tackle them, but if a little more patience might raise the odds in our favor while lowering the cost to try, and with the reminder that the public may say it will embrace risk, but the real result of losing a 50-50 mission is not just a hesitation to try again in a couple years when the next launch window opens. A spectacular failure might require a couple generations before enough people get on board to try again. I believe we could still get it done, and probably more robustly if that happened, and I have no doubt we would find plenty of willing and capable volunteers for either mission. But that's hardly an ideal approach, and it's a good reminder that there's little margin for error. Given the challenges, it is wise to optimize every variable you can. First and foremost, Mars is distant. A lunar base sits only 3 days away, within real-time communication and quick resupply range. Mars is 6 to 9 months away at best, with rescue measured not in days but in years. A lunar mission that runs into trouble can plausibly be patched, rescued, or evacuated. A Martian mission that falters is on its own. No mission planner, no crew, and no civilization should want its first permanent settlement to be one where help cannot arrive. Even for the Moon, as much as I want a permanent presence there and believe will help us reach Mars, I still prefer we get another full-time crewed space station into orbit. Ideally one we can attach a moonship to that's fully fueled, since we cannot launch a rescue mission if the weather down here is terrible. I am a big believer in tackling problems with overwhelming force and a catalog of contingency plans. I may be too cautious, but even as a huge an advocate for space settlement as I am, I do not see a huge urgency to make it happen quickly, merely a need for relentless and robust forward motion. Second, and this applies to the Moon too, the popular worry about us blowing ourselves up and needing another planet so we don't have all our eggs in one basket is honestly not a good one. We lack the weaponry to turn Earth into an inhospitable wasteland, and even if we nuked this planet so hard it glowed in the dark, it would still be easier, cheaper, and faster to make it habitable for humans again than Mars, the Moon, Venus, or any other rock in space. We would need vastly superior energy sources or vastly superior automation to be able to wreck the planet that badly, yet both also make reaching other worlds much easier. Now, in the case of a bioweapon, somebody might yet come up with a COVID on steroids epidemic for us that could basically get everyone, but even then, you can protect against that with an airtight living quarters and suit, which is a pain, but you need that on Mars too, and you don't have to ship the equipment 100 million miles first, so even here, it's still easier on Earth. Moreover, with the exception of hyper-rare events like supernova, no candidates for which are nearby us, or some unspotted rogue dwarf planet ramming Earth, which is possible but highly unlikely, all the true extinction level threats to humanity come from humanity, or something we might create like gray goo or an AI. Having another planet certainly doesn't hurt in such cases, but by and large, those are threats you export wherever you send humans. Gray goo can't climb its way out of Earth's gravity well to get to a moon base, any better than it could get to Mars, and an AI able to wipe out all humans on Earth is not going to have a problem building ships to get to the moon or Mars either. So yes, we do want to get our eggs out of a singular basket, but the necessity and practicality of that gets a bit overstated. Plus, a Mars base of 10 people isn't achieving that goal anyway. Third, Mars does not offer us anything unique. Its resources are not richer or more useful than those on the moon, in near-Earth asteroids, or in Earth orbit. Everything we could hope to mine on Mars exists closer and easier to reach. A Martian colony will need Earth, the moon, and orbital industry for support, but none of those need Mars. For building up a spacefaring economy, Mars is a latecomer, not a keystone. Fourth, and perhaps most crucially, is the problem of gravity. Mars has 38% of Earth's pull. That feels appealingly close to normal compared to the moon's 16%. We simply don't know if it's enough. We do know it is enough to make it an economic pain to leave, compared to the moon or asteroids, but we do not know if it will be a pain to physically endure. Long-term health in partial gravity is an unanswered question. Children raised in it might grow bones too light to survive Earth's pull. Adults might deteriorate in ways exercise cannot offset. And until we know what humans can actually withstand, founding a permanent settlement at 38% G is an enormous gamble. For my part, I tend to suspect 38% plus exercise and supplements will be enough, even for many years, if not a lifetime, and we tend to take for granted that it will be endurable longer than 0G, which astronauts have experienced for a year at a time. But a trip to Mars and back would take much longer than a year, and the simple reality is that we do not know. That knowledge can only come from two places: the moon and artificial gravity. A permanent lunar base will teach us whether humans can adapt to 16G long term. If we thrive there, Mars becomes a safer bet, as does Mercury, which has the same gravity as Mars, Venus, which has more, Saturn's giant moon Titan, and the Galilean moons of Jupiter, whose gravity is parallel to our moon's. Perhaps we'll find out the moon is not enough, but Mars and Mercury are. If not, then we must embrace spin habitats, vast rotating stations that create Earth normal gravity, or anything in between. Only by building such environments and testing at levels like 38% can we know whether Mars offers us a healthy future or merely a prolonged compromise. We will want them for the trip too, so they are not in zero gravity. And in my opinion, I view spin gravity habitats as more central to humanity's future than planets anyway, and a spaceship being built for Mars with a spin section designed to give some gravity during the trip can act as a test site and training ground for that mid-range gravity while being outfitted and tested, all while automated ships go pre-stage supplies in Martian orbit and even groundside. Most of those supplies are bulky and durable stuff, particularly fuel and radiation shielding, which might be gotten from the moon cheaper than dragged up from Earth. This is why the moon must come first, not because it's more glamorous, but because it's more practical. It's where we can test technologies, closed life support loops, mine and manufacture off-world, and establish whether our bodies can endure reduced gravity. It's a laboratory, a logistics hub, and a launch pad, all within sight of Earth. It is the foundation stone of a true spacefaring civilization. Mars, in contrast, is not a foundation stone. It's a milestone, something we can and should aim for, but not before we've built the scaffolding of lunar bases and orbital infrastructure that makes it survivable and sustainable. To race to Mars now would be to plant a flag on Everest before we've ever climbed a hill, stirring in symbol but unwise in substance. Mars will wait. It's waited 4 billion years. What's a few more decades? Humanity is at the dawn of its cosmic age, and we need to learn to walk steadily on the moon before we can stride across the red sands of Mars. As we weigh the pros and cons of colonizing Mars, one thing's clear. Wherever humanity goes, our technology follows. And that's what my new Nebula exclusive explores: autonomous space industry, when AI and robots run the economy. We look at how robotic factories, AI management, and self-replicating industry could help the first pioneers of the solar system by building basic bases and even entire outposts or habitats before humans arrive. While you're there, check out Scav, Nebula's newest original series for the Wendover team. Every year, a 20-page scavenger hunt list plunges the University of Chicago into fun, sleepless chaos, and Scav follows 3 top teams through 4 days of creativity, absurdity, and brilliant problem solving. Nebula is ad-free, creator-owned, and home to some of the most thoughtful and entertaining work you'll find online. Get a lifetime membership, normally $500, for just $300 with my link go.nebula.tv/IsaacArthur, or 40% off an annual plan for just $36 a year. Scan the QR code or click the link to start watching now. If I had $1 trillion. Over the years, I've often got asked what I would do in space if I had an effectively unlimited budget, and my answer is, I still wouldn't rush it. Unlimited funding doesn't remove the risks of hurrying. Throwing money at problems has limits, especially when it comes to quality control, reliability, and the gradual experience that long-range missions demand. That's doubly true when we're talking about something as ambitious as Mars. If I had a giant but plausible budget, say $1 trillion, the first step would be to build a new modular space station to replace the ISS. This wouldn't just be a laboratory to visit, but a proper waypoint in a dockyard. I'd give it a thick, hollow outer shell for storing water and fuel, doubling as radiation shielding. It should be a place to store supplies, refuel spacecraft, and assemble new ones, as well as the foundation for later stations and ships. While that's underway, I'd be dropping rovers onto the moon, not just to scout landing sites, likely in the South Polar region, but to learn how lunar regolith wears on machines and to build practical experience with operations there. The next phase will be running a shuttle service from the new station around the moon, dropping pods of equipment and supplies to the planned base site. After establishing a steady delivery system, we'd land crews to assemble the first permanent base, sized for at least 20 people. The transport ship never sits idle, except for refueling and maintenance, and as soon as possible you would build a second to keep the flow constant. Fuel choice matters. From day one, you want the moon base practicing in situ fuel production, whether from ice deposits or regolith, because Mars is not the place to discover that a crew of 6 cannot manage it. Power systems should likewise be redundant, both solar and nuclear. Everything is a learning mission. On the moon, you're learning to make soil from regolith, grow food locally, manufacture fuel, and discover how many crew are truly needed to balance scientific and settlement work. On the space station, you are practicing hydroponics, spacecraft assembly, and ship repair. You learn by operating the shuttles, servicing satellites, and eventually assembling the rotating station that will itself become a spaceship. You get it spinning early to learn how to dock with it and work in a rotating environment. Once those systems are proven, you begin launching supplies for Mars during favorable windows. That rotating station is gradually packed with fuel and water hauled up from Earth or mined from the moon, both as consumables and as shielding. Durable cargo goes first. The crew follows only after advanced supplies are confirmed, and even then, you might punt the first crewed opportunity, sending more probes and equipment instead, while you continue gaining long-term operational experience. Various mission elements can be run in parallel rather than sequential too, but if this is what happens, you build another space habitat and expand the crew, adding more living space rather than pulling people back home. Life gets much easier if we confirm usable water on Phobos or Deimos, or perfect regolith-based fuel production on the moon. We need to test both, because Mars must not be the first trial. When the time finally comes to launch a crewed ship to Mars, most of it never comes back to Earth, except maybe fleetingly. These are not disposable capsules but permanent infrastructure. Some will become Aldrin cyclers, shuttling back and forth between Earth and Mars, perhaps with nuclear power to maintain their orbits. Others might remain in Martian orbit as stations or be docked to the Martian moons. The premise is the same as the moon: no backward steps. Once you know how to build bases, stations, and ships, you just keep building more. Each iteration gets cheaper, easier, and more reliable. Every rendezvous of a shuttle with a station or cycler goes with some excess fuel, water, and air reserves, and that excess just keeps accumulating as more radiation shielding and more reserves on those stations and cyclers. Ideally, the first Mars ship rendezvous in orbit and remains there, the next one or two becoming cyclers. Crews would ride these cyclers out and shuttle between them and Mars orbit, then on down to the surface. By then you're producing fuel locally on the Moon, on Phobos or Deimos, and on Mars itself. Personally, I would never send a human being beyond cislunar space until I was confident we can reliably manufacture thousands of kilograms of propellant in situ, under real conditions, vacuum, dust, abrasive regolith, not just in earthbound labs. Because unlike the Moon, where rescue is possible, Mars is too far to gamble on untested systems. So the critical question isn't if we should go to Mars, it's when. We should only go when we can do it robustly, not a flag-planting mission of 2 or 4 astronauts hoping to make it back, but a permanent settlement of a dozen or more from the start, with multiple cycler ships constantly ferrying people and supplies so we're not trapped by launch windows. Done right, the first crew to land on Mars will not be pioneers hoping to survive, but settlers joining a chain of stations, bases, and ships that make their presence lasting. Not necessarily permanent, but certainly not short-term either. Aldrin cyclers work best in complementary pairs or more, one serving as the up escalator, the other as the down. See our Aldrin cycler episode for more on the various options. Done this way, the actual transit between Earth and Mars, or vice versa, can be brought down to about 5 months, with plenty of opportunities for additional cyclers and their launch windows. And if you got serious fuel production operating in both cislunar space and Martian orbital space, rather than only on the surface, then even faster ships become viable, especially if nuclear propulsion is on the table. And here's the key thing. This mission approach and architecture all works very easily to scale up to send more folks to Mars or the Moon, or to shift to other planets and moons. And this answers our question, not should we go to Mars, but when. And the answer is when we're ready to stay there, and to go to other places too. We do not go to visit new worlds. A robot can do that. We go there to claim them for all of mankind as a new home for humanity. A slow but relentless process of growth and learning that permits no failure, no backward step, only onward to the next horizon. Thanks for watching, and until next time, have a great week.